All right, so just as I brought up in the last lesson, you have to differentiate with parametric equations. You are also going to have to integrate with parametric equations. You're going to have to do the same thing that you would in any other case. So you're going to want to find the area under the curve, and you'll also want to be able to find the length. You'll want to find the area between curves. And again, the formulas follow from our basic understanding of x and y. It's just that the x and y are separate equations versus just being the same. So in the case of A, for the area underneath a curve, what we're used to is having the integral from a to b of y dx. Usually we don't write y, usually we'd write this as f of x, but as we've discussed, f of x and y are interchangeable. So what this means is that the formula follows pretty naturally from that, except for we are dealing in terms of t. And so the y there becomes the integral of y of t. We're going to use that function here, the y of t. And then dx, well, that's dx dt. And then dt again, if we think about, again, Leibniz notation is really helpful here, because then those cancel out, leaving behind our dx, which is what we want. But then we can integrate in terms of t, which is the actual variable we're using. And it also allows us to leave our bounds, alpha and beta, are values of t, which is really helpful there. So, when we're looking at an example, find the area under the curve of one arc of a cycloid defined by x of t equals t minus sine t, and y of t equals 1 minus cosine t. So the first thing I would do is I would graph this on my calculator, just like we talked about in our last lesson. And what you'll see on the calculator is, let's try to draw that a little bit better. You will see an arc here that's going through stages. I'm zoomed out a little bit. And so when they say one arc, they're asking for, oh, what's the area underneath here? And since we're looking here to here, I mean, you could have picked any one of these. I think that that one is the, not the obvious, but the sort of natural one based on our understanding of mathematics to pick. That's what I would do. To find those bounds, I would say y is equal to 0, since we're looking at where it's ending on the x-axis in both cases. So if y is equal to 0, that just means we want to solve the equation where 1 minus cosine of t is equal to 0. So where cosine of t is equal to 1. Now cosine of t equals 1 at infinite points. The ones that we're looking at here are t equals 0 and 2 pi. So here is t equals 0, and then it comes back down again at 2 pi. The next would be at 4 pi, etc. So you could find, when we set up the bounds, I'm going to use 0 to 2 pi. You could use 2 pi to 4 pi. You could use negative 2 pi to 0. All of these would be fine. Now you're going to take your y value, so 1 minus cosine of t, and then x prime, so our derivative here, 1 minus cosine of t, which is our dx dt. So times that dt. And that's the actual integral that you want to be differentiating. What I would do in this case is expand it out, and I get 0 to 2 pi and 1 minus 2 cosine of t plus cosine squared of t dt. We can solve this with substitution. Everything else is pretty straightforward with differentiating. I am going to jump ahead to the answer if you would like to check yourself. To keep this video from being too long, we end up with the area under that curve is 9.425. Now the other thing that you'll be asked to do with parametric is to find the length of the curve of the cycloid. So the cycloid is the picture from above. We're going to use the same functions. Now if you recall, length of the curve function is just coming from the distance formula. So if you remember, the distance formula is the square root of the difference in x values plus the square root of the difference in y values. So in this case, that's dx squared plus dy squared. And since we're in terms of t, so dx dt squared plus dy dt squared. And if I put those into the denominator, so if I want to have a dt squared in each of the denominators going in here, that's dt on the outside, dt like so, to keep the fraction equal. That's how you end up with dt here, so that we can actually integrate in terms of t. So again, these are just coming from algebraic expressions that you're familiar with, and it is just using the distance formula. So in this case, we'll use the same functions as above. So dx dt, or x prime, as we previously said, is 1 minus cosine of t. Y prime, or dy dt, would be sine of t. So then the length of the curve, it's for one cycloid, so again I'm going to pick 0 to 2 pi, but you could pick whichever one you like, is root dx squared, so 1 minus cosine t squared, plus sine of t squared. Now you could use your calculator right here, but let's do a little practice with simplifying. 1 minus cosine squared is 1 minus 2 cosine t plus cosine squared t, then plus sine squared t. As I would hope that you recall, cosine squared plus sine squared is just equal to 1, so we can add that to its like term, and this becomes the integral of 2 pi from 2 minus 2 cosine of t in the root. Again, I will jump ahead to keep this video from being too long. You can do algebraic substitution here, and the correct answer is 8. You can also use your calculator if it is a calculator problem. So again, you've got your two new formulae to deal with integrals, both area and length, using parametric equations. And please reach out if you're stuck on anything or you would like assistance. Talk to you later.